Hi folks, welcome to the next installment of Electric Fields. This is part 4 where we look at electrical potentials. And what do we got here? Okay, well what we mean by electrical potentials is that basically it requires work to be done, work in terms of the physics sense, to move electric charges within an electric field if a force is being experienced. So electric charges can gain or lose energy depending on their position within an electric field. The force that has to be overcome is the Coulomb force, which we can calculate using Coulomb's law. So what we have here in this diagram, let's see if I can get my pen up. There we go. What color are we? Blue. We have a charge here which is positive and it's generating the electric field. We have another little charge here which is also positive, and we're going to, if we move it from there to there, we're actually doing work. Work is being done because we're being opposed by this force here, which is the Coulomb force. Now we're also moving it from here to here, so we're getting a change in the electric field strength which correlates to that gain in potential energy, or the work being done, which is also measured in joules. If however we have a charge over here which is the same, but we're moving it in a circular motion where it's not experiencing a force, in this case we're experiencing a force of repulsion. Here it's experiencing a force of repulsion, but we're not moving it against that force, we're moving it 90 degrees to that force. No work is done. Okay, so slightly different situations. In this case we can calculate the work done. In this case we don't have to calculate the work done because there isn't any. So let's just do a couple of examples. Students often get confused by this. I get confused by it sometimes. So we'll do a couple of examples just to work it out. Okay, so here we have W representing work equals the charge times by the electric field strength times by the distance that we're moving it, and so work is done, and the work done is stored as electrostatic potential energy. What's the unit of energy? It's in joules, and it can be used to give the charge kinetic energy, so make it move, or basically that's what we predominantly use it for. Work done is in joules, the charge that is being moved, the electric field strength that the charge is experiencing, and the distance being moved. And so all this is derived from W equals Fs, because F is equal to QE in our electric fields. We've seen it more familiar as E equals F on Q, but F equals QE as well. So here we have a diagram. Let's explain it. The electrical potential V is the electrostatic potential energy stored per unit charge at any point, given point D, from a charge Q. So there's our charge Q. There's our distances. We're moving it from V1 to V2. Now V is not velocity, it's voltage or potential. Remember that potential difference is given by a capital V as well. So moving it from infinity, and then eventually you get it towards the electric field, we have a change in the potential voltage. So the unit of V is volts, obviously, or joules per coulomb, equally valid. And the potential difference is the work done in moving a unit charge from position 1 in the field to position 2. So from there to there. So it's changing its position in the electric field, and so work is being done. And so we can look at this calculated thing. The change in the voltage is V2 minus V1, which equals the work done moving it from 1 to 2 divided by Q, the charge, which equals the work done moving it from 1 to 2 equals the charge times by the change in voltage, because W equals QV, and therefore we equals W equals Q V minus V2 minus V1 times by Q. complicated. Now you have to remember some of these formulas because unfortunately they're not on your information sheet. Therefore, the voltage V equals work divided by Q. Now work is given by QED, which we saw before, and ED, this can simplify in down to ED because these two Q's cancel, and so V equals ED, and given that E is equal to KQ on R squared, which we did before, times D and R are the same. Alright, D and R are the same, so we can cancel that and we get V equals KQ on D, which is a slightly different formula from this one here, so students get confused as to which formula to use. First question you've got to ask yourself is, what do you want to find? And this is just recapping that V, because we've said work can be anything. It can be a change in kinetic energy, or in this case a change in the potential energy. And so work, as long as it's in joules, it can be any form of work. And because E equals V on D, alright, we've got this one here as well. Alright, so you need to remember that, or try and work it out if you can. Let's do a couple of examples. It gets very confusing here. We've got the 2-point charges A minus 6.5 microcoulombs, B plus 8.3 microcoulombs. We've got a midpoint, and find the potential at the midpoint between their centers. And so again, you take it as if you make one of them disappear, get rid of B, I'm trying to make it disappear on the screen, and you just work out the potential due to A as if you're ignoring B, and then you work out the potential due to B as if you're ignoring A, and then notice that one's minus, one's positive, because they've got a positive charge and a negative charge, so you have to work out the direction and define one way as positive and one way as negative, and then you do vector addition and you get the answer. Pause this and have a read of this, make sure you understand it. It's also in your textbook. In this case we've got two plates and we've got our uniform electric field going from the positive plate to the negative plate. That's how we define it, and we've got V equals the work done divided by Q. We can rearrange it into work equals QV. So if we know the voltage across here, which is in this case 20 volts, and we know the charge, for example an electron, we can work out how much work is being done moving it from here to here. Now these lines here are called equipotentials, and they're zones that have the same potential difference, or in the electric field. So what have we got here? The test charge Q will also experience a force in the field, and work done against this force would move the charge across the place. Saturation is given by W equals FD, which is effectively W equals Fs, work equals force times distance, and where F equals QE, we can substitute that in. So lots of formulas, lots of letters. This is what usually throws students, so just be careful and think about it, do a few questions and you'll get the hang of it. What have I got? Lines of equal potential. So if we magically made an electron pop up here, it would actually have to do less work going from there to there than if it popped off this plate and went the whole distance, because it's crossing less potential different lines of equal potentials or equipotentials. Very complicated. Okay, so thus within a uniform electric field we can say that Q, the charge, times by the voltage equals Q times E times D, where E is the electric field strength, which is constant because it's a uniform electric field, equals V, rearrange that, V equals ED because the Q's cancel, and rearranged E equals V, where V is the voltage between the plates that causes the uniform field, divided by D, which is the distance between the plates. So we can work out the strength of the electric field between two plates by that formula there. And that can be given as either volts per meter, okay, volts divided by meters, or in Newton coulombs. The units are equivalent. What do they look like? These dashed lines and these figures are areas of equipotentials. So if you go across any of those dashed lines, work has to be done. If you go along any of those dashed lines, no work has to be done. The electron volt, EV, is something we're going to have to start using. It's a measure used in atomic physics. It's a measure of if an electron moves across a potential difference of 1 volt, so two plates with 1 volts of potential difference, how much work is done? 1 electron volt is done. And this is the formula, W equals QV. There's the charge of an electron moving across 1 volt equals 1.6 times by 10 to the minus 19 joules. So 1 electron volt is 1.6 times by 10 to the minus 19 joules of energy. And so when we're talking about particle accelerators and things, they're measured in giga or tera electron volts. And when you hear about the LHC colliding, looking for the Higgs particle and stuff, it's talking about its energy in terms of electron volts. So you should be able to now do those questions out of your booklet and have a go at them. And next video we'll look at the Millikan oil drop experiment. Cheerio!